The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so basic probability ideas today, because that's a part of the subject, part of deep learning as we get there. And it's probably a good topic for the day before spring break, because lots of you will have seen, of course, you will have seen the sample mean, the average of the data. So we have, and you'll know about the expected mean. Let me complete that. What's the expected mean? So this is the expectation of the value x, where we get x1 with probability p1 along to xn with probability pn. So we just want to say what's our average output, average outcome, and we weight it by the probabilities. So it's p1 x1 plus so on plus pn xn. So that's the expected value of x. Are you comfortable with that symbol E? Because that's like everywhere. It gives a handy shorthand. For example, the variance is the expected value of what? The variance is an expected value based on these probabilities of the square of the distance. So everybody remembers it involves square, and it's the distance from the mean. Let me call this, say, M, maybe, just to have a smaller letter, but I could put it, so it's the distance from the mean minus M. It's the expected value, the average value of x minus m squared. And in general, of course, this covariance matrix I could express with that E notation. But let me just stretch it as far as what would be the expected value of any function of x? Well, we've got n possible outputs, x1 to xn. We look at f of x1 up to f of xn. We weight those by the probabilities that they happen. So this would be, let me make just a little corner for this E letter. So this would be the probability that that is f of x1 times the value f at x1. So this is the contribution from the x1 possibility, and now we include them all. So it'll be f output f of xn with probability pn. And if that f of x is x minus m squared, then we get what we expect, and let me remember that. So I just want to keep going with variance. So it's the sum, it's the first probability times the first output minus the mean squared. The last probability times that last output, xn minus m squared. And everybody should know a second expression, a second way to do that sum. It's just, if I just write out those squares and combine them a little differently, I get a second expression which is really useful, often a little faster to compute. So can I just do that? So that's x1 squared minus 2 x1 m1 plus m1 squared, right? And then same thing here, pn times xn squared minus 2xn m plus m squared. Good with that? Sorry? Plus n. Oh, sorry. No, I mean, am I? Oh, it's just an m. Correct. Thank you. Thank you. Just an m. Good. Okay, can we take that sum? So I get p1x1 squared. If I take these, the first guys, so I've accounted for this and this, and now I'll take minus 2 p1 x1 m, so p1 x1 m plus pn xn m. I'm just writing it all out, and I'm going to recombine it. So now I have p1 m squared plus p2 m squared plus pn m squared. So what do I have from the p1 m squared all the way up to pn m squared? Are you with me? So m squared is in every term. So I'm going to have an m squared. And what's it multiplied by? P1 here, P2 here, Pn here. I add those up and I get 1. So that's it. Okay, and now I'll just simplify this thing. So this is really the expected value of what? What am I seeing in this term? The expected value of x squared, right? Different from the expected value of x minus m squared, of course. This is just the first term from here. But now what do I get for this second term? Well, the point is that m comes out. So this is minus an m and a 2. And what do I have left? So I've used up the m. I've used up the 2. p1x1 plus pnxn. What's that? Everybody should just pay attention to this. Trivial. I mean, we're just doing high school algebra here. But p1x1 up to pnxn is m. So I have another m squared there, and I have a plus m squared from the end. So you see that it is another expression, the expected value of x squared minus m squared. Just algebra, that is the same as this. So that if you happen to have a handy way to compute the expected value of x squared, you would just subtract m squared and you'd have the same as this. Yeah, it's just algebra. Okay, let's go a little deeper with something here, if I can find it. There are two great inequalities in statistics. And the first one is due to Markov. And I don't know if you know Markov's inequality. It comes out easily. In fact, too easily. I'm kind of happy with the discussion in this. Now I'm jumped to section 5 of the book. So I'll need to post section 5, which is probability and statistics. And you'll see this Markov inequality. So it just involves this stuff, so that's why I'll go to it now. Markov's inequality. He was a great Russian mathematician, well, probably about 1900. And we will see Markov chains and Markov processes. That's beautiful linear algebra. But this little inequality is not matrices. It's just playing with these. But and it applies to to non-negative events. So I'm going to, when, shall I say, applies when all the outputs are greater or equal to 0. So it's going to be I'm going to use that fact. So it doesn't apply to something like Gaussian, because they're Gaussian, the outputs go all the way from -infinity to infinity. It does apply to a lot of important ones and simple ones. So I'm just saying, let's suppose, I'll give the proof for this finite probability, and there'd be a similar proof, similar discussion everywhere here for continuous probability. So what does Markov say? Let me be sure I get it right, because I'm not a pro at this. It's natural to want to estimate the probability that x is greater or equal to some number a. Get some idea of what's the probability of x being greater or equal to a. So what do we know? This is certainly a number between 0 and 1. That number is going to get smaller as a increases, because we're going to be asking for more. If I take a to be, say, twice the mean, or yeah, suppose I take a to be twice the mean. Can I estimate what that probability could be? And that's what Markov has done. He says the probability of that is at least, at most. Sorry. Let's see, I used to have an eraser. At least, or sorry, at most, yes, got it, is less or equal to the mean. X bar is another way to write the mean, divided by a. And this is the mean over a, or it's the expected value of x over a. We could see any of those notations. Okay. And as we expect, as a increases, the probability, this number goes down, the probability goes down of exceeding a. So that's a pretty simple estimate to get this probability just in terms of the number a, which has to come in because it's part of the question, and the mean x. Okay, so let me take an example as a equals 3. Okay. So I'm going to just, for example, suppose a was 3. I want to show that the probability of x being greater than or equal to 3, yeah, okay, so we don't know, we don't have many facts to work with, so if we write those down, we should see the reason. Okay, so I know that the mean is e of x. So let's see, am I going to take, yeah, I'm going to, for example, let's take the mean to be 1. Okay, so I'm going to imagine that the mean is 1, and that I'm asking for what's the chance that x will be bigger than 3, and I'll get an estimate of 1/3. So I'm trying to show that the probability of x greater or equal to 3 is less or equal to the mean, I'm saying, is 1, a is 3, so it's less or equal to 1/3. Now, why is that true? That's what I have to show. Okay. I think that if I write down what I know, I'll see it. Okay. All right. So let me Let me just raise that a little so that I have room to write. So what do I know? I know the definition of the mean. So I know that x1 times p1 plus x2 p2 plus x3 p3. Allow me to get carried away here. x5 p5, say, is what? So what I've written down there is the mean, and I'm assuming that to be 1. So this is the fact that I know is 1. And what is it that I want to prove? I want to know the probability of being greater or equal 3. So what's the probability that the result will be greater or equal 3? It's P3. So this is saying that P3 plus P4, these are the probabilities. These are the different ways that I might be greater or equal 3. And I'm claiming that that's less or equal 1/3. What I liked about this elementary approach is that I've stated these facts, these probability assumptions and conclusions directly in terms of numbers. So I just want to show that if this is true, then that's true. Let's see. I guess I'm thinking that I'm sorry, I even took a more special case. I'm taking the case where x1 is 1, x2 is 2, x3 is 3, x4 is 4, and x5 is 5. So that satisfies my condition that the outputs, 1, 2, 3, 4, or 5, are all Markov only applies when they're all greater or equal 0. So I had to so I'm just imagining the special case where the possible outputs are 1, 2, 3, 4, 5. Their probabilities are P1, P2, P3, P4, P5. The mean is 1. And what I want to show is that the probability of being greater than 3 is less or equal 1/3. And can you put together these two? Can you conclude, given this, we want to conclude that? Let me just step back a minute. So what do we know here? We know this, the first line, and we want to prove the second line. We know one more thing. All the probability, well, we know the probabilities add to 1, and we know they're all greater or equal 0. So let me put those facts in here too. We know that P1 plus P2 plus P3 plus P4 plus P5 is 1. That we know. And we also know that all the P's are greater than or equal 0. Okay. Okay. So here we go. I think my idea is this is looking at 3 times P3 plus P4 plus P5. So I'm going to take 3P3 plus 3P4 away from this. So this will say P1 plus 2P2 plus 3 of P3 plus P4 plus P5. I'm just picking out 3 of those guys. Plus, I have 1 more P4 to account for, and 2 more P5s gives 1. Okay. Good? Now, this is what I'm trying to prove. So that is here. I'm trying to prove that this thing is, what am I trying to prove about that number? Can you, sorry, I'm talking a lot, but now I've really come to the point. What is Markov telling me about that number that is less or equal to? Thanks. Okay, I'm trying to prove that this is less or equal 1. That's what Markov tells me. But suppose it was greater than 1. Do you see the problem? Do you see why it can't be greater than 1? Because why? All the other terms are greater or equal 0. Probabilities are greater or equal 0. These are all greater or equal 0. And the total thing adds to 1. So that this piece has to be less or equal to 1. That's right. That's it. So a lot of talking there, simple idea, and you'll see exactly this example written down in notes. Okay. And then you'll see a more conventional proof of Markov's inequality by taking simple inequality steps, but they're somehow more mysterious. For me, this was explicit. Okay. So that's Markov. Chebyshev is the other great Russian probabilist of the time, and he gets his inequality. So there are the two. There's Markov's inequality. Let me write it down again, what it was. Here was Markov's inequality and Markov's assumption. Chebyshev doesn't make that assumption. So now, no assumption of that the outputs are greater or equal 0. Doesn't come in. Okay, now what is Chebyshev trying to estimate? Okay, let's move to Chebyshev, and that's the last guy. So Chebyshev is interested in the probability that x minus the mean, m, can I use that for mean, is probably greater or equal to a, the probability of being sort of a distance a away from the mean. So again, as a increases, I'm asking more. I'm asking it to be further away from the mean, and the probability will drop. And then the question is, can we estimate this? So this is a different estimate, but it's similar question. And what's Chebyshev's answer for this? So this is the probability of this. I have to put a big, that's all one mouthful. The probability of being that this x minus m is greater or equal to a. Okay, and again we're going to have is less or equal to sigma squared now comes in over a squared. So that's Chebyshev. And I just take time today to do these two because they involve analysis. They're basic tools. Is sort of the first thing you think of if you're trying to estimate a probability. Does it fit Markov? And Markov only applies, so I'll put only applies when the x's are all greater or equal 0. Here, does it fit Chebyshev? And now we're taking absolute values, so we're not concerned about the size of x, and we're taking the distance from m. So we're obviously in the world of variances. We're distances from M. Okay. And the proof of Chebyshev comes directly from Markov. So I'm going to apply Markov. So good thing that Markov came first. To, now let me just say this right, to a new, let me call it Y. This will be a new output, and it will be x minus m squared. So that's, if I, of course, with the same probability. So yi is xi minus m, the mean, squared, and the same probabilities pi. Okay. So I guess if I'm going to apply, I'm just going to take that as, take the y's here instead of the x's here. So, and then apply Markov. So what is x bar? So if I want to apply Markov, I have to figure out the mean of x. Over here, I have to figure out the mean of y. What is the mean of y? The mean value, the sum of probabilities times y's. You're supposed to recognize it. This is the sum of probabilities, and my y's are the xi minus the mean squared. So this is the mean for this y thing that I've brought in, has that formula, and we recognize what that quantity is. That's sigma squared for the original x's. So that's great. So the mean is sigma, is the old sigma squared. Those are exclamation marks. Okay, so then do you see that now Markov is looking like, or Chebyshev is looking like Markov? Because here, over here will be now I want the expected value of y over the, let's see. Yeah, so the expected y is going to be that. And now what do I have to divide by? I want to know probabilities of something being bigger, of this thing being bigger than a. But now I'm looking at the y's. So the probability of, if x minus m is greater than or equal to a, then x minus xi minus m squared is greater or equal to a squared. So my a over here for x is now turning, in this problem, where I'm looking at probability greater or equal to a, but squaring it, this is the a squared. So that's Markov applied to y. Here's Markov applied to x, and x had to be greater or equal to 0. So over here, Chebyshev took a y, which was greater or equal to 0, then just applied Markov and recognized that the mean was of his variable, x minus m squared, was exactly sigma squared, and it fell out. So again, here is a very simple proof for Markov, and then everybody agrees that Chebyshev follows right away from Markov. Okay, so those are two basic inequalities. Now, the other topic that I wanted to deal with was covariance matrix. You have to get like comfortable for what is that? What's the covariance? Okay. Okay, so covariance matrix. And it will be M by M when I have M sort of experiments, M at once. Well, let me take M equal to 2. You'll see everything for M equal to 2. So we're expecting to get a 2 by 2 matrix. And what are we starting with? We're doing 2 experiments at once. So we have 2 outputs, an X and a Y. So the X's are the outputs from the X experiment. The Y's are the output from a second experiment. We're flipping 2 coins. So let's take that example, 2 coins. Coin 1 gets 0 or 1 with P equal probability of half. Coin 2, 0 or 1 with probability of half. So they're fair coins. But what I haven't said is, is there a connection between the output, this is the X, this is the Y. If I glue the coins together, then the 2 outputs are the same. I think for me, this is a model question that brings out the main point of covariance. If I flip 2 coins separately, quite independently, then there's no, I don't know more about Y from knowing X. If I know the answer to one flip, it doesn't tell me anything about the second if they're independent. Uncorrelated. But if the 2 coins are glued together, then heads will come up for both coins. It'll be, I'll only have 2 possibilities. That'll be heads, heads, or tails, tails. Let me write down those 2 different scenarios. So unglued, I never expected to write that word in a math class, unglued. And what am I going to write down? I'm going to write down a matrix with heads, tails for coin 1, and heads and tails for coin 2. So the possibilities are coin 1 gets heads and coin 2 gets heads. What's the probability of that? This is the unglued case. So I'm going to create a little probability matrix of joint probabilities. That's really the key word that that I'm discussing here. Joint probabilities. So let's complete that matrix. So I have unglued coins, independent coins. I flip them both. What are the chances of getting heads on both? 1/4. What are the chances of, what do I put in here? This means heads on the first coin and tails on the second coin. And the probability of that is 1/4. And 1/4 here and 1/4 here. So I have the 4 possibilities, which I put into a 2 by 2 matrix instead of a long vector. My 4 possibilities are heads, 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 tails, tails, heads, and tails, tails, and they have equal probability 1/4. But now if they're glued, heads and tails on the first coin, heads and tails on the first coin, heads and tails on the second coin. Okay, Now what do I put in there? So the two coins are glued together. What is the chance that they both come up heads? 1/2, right, 1/2. Because if one comes up heads, the other one is glued to it, it will also. What's the probability of heads, tails? Heads on one, tails on the other is, of course, 0, thanks. And here 0, and here 1/2. So what I've created are those two two different setups, two different scenarios of unglued and glued. And in this one we have, but each experimental setup has its matrix of joint probabilities. That's the thing, that there are 4 numbers here, 4 numbers. We have all possibilities. We have any possible x, and at the same time any possible y. So suppose we were running 3 experiments, and we had so what would be the situation if I was running 3 experiments with 3 independent fair coins? So I'd be in this unglued picture, but I would have 3 different experiments that I'm running. Then what would I be looking at then? Just the whole idea is to see what is this like joint probability. So suppose I have 3 coins unglued, then I want to know like the probability of getting heads on the first, heads on the second, heads on the third will be what? Just to give me that number. What will be the probability of that all 3 of them independently come up heads? 1/8, okay. But now my question is, so what do I have? Then I have probability of heads, of say tails, heads, heads. I've got 3 indices here, eventually down to probability of tails, tails, tails. Everybody sees at the end the numbers are going to be 1/8, but where do those fit in? They don't fit in a matrix because I've got 3 indices here. So I guess that we're seeing, I sort of realized today, we're seeing for the first time a tensor. A tensor is a 3-way structure, 3-way matrix, you could say. So we have, I guess I think of this instead of a square like that, an ordinary matrix. I have to think of a cube, right? I have a cube with 2 rows, 2 columns, and 2 whatevers. Layers, somebody might say layers for that. Do you see that the matrix has become a a 3-way thing, a tensor. And the entries in that tensor, so it's 2 by 2 by 2. That instead of m by n for a matrix, I have to give you the number of rows, the number of columns, and the number of layers going into the board. So rows going one way, well, you know, columns, rows, and then layers are going in deep. So it will have 8 entries. And of course, in this simple case, each will be 1/8 in that unglued, totally independent way. But then you can imagine some dependence. Say, well, so what would happen if I glued coins 1 and 3? I would still have a tensor, still have a 2 by 2 by 2 tensor of all the possibilities. Now, but some of those are going to have probability 0, the joint probability. If I've glued coin 1 to coin 3, then the probability of jointly seeing heads on 1, whatever on 2, tails on 3 will be 0, right? Because that can't happen if I've glued coins 1 and 3. So I'll have 8 entries in here. This is the unglued case. And then I could have the case where 2 coins are glued. And as I say, I think I would have 4, I'd have 1/4 4 times probably. And then if I had any spare glue, I glue all 3 coins. I flip that stuck together thing, and I never get heads, tails, heads, right? Only possibilities I get are heads, 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 and tails, 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 because they're glued together. So what would be the situation for 3 coins glued? What will be the entries in the joint, in the matrix of joint probabilities? What will be the joint probability? So the probability of heads, 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 of seeing heads from all 3 will be a half, because I'm flipping this heavy mix of 3 coins together. I get 1/2 twice. Okay. Actually, this is a good introduction to tensors in a way, because the first step in understanding tensors is to think of 3-way matrices. Think of 3-way things. We just haven't done that, and now we have to do it. And of course, 4-way or n-way tensors are now understood. Okay. So these are tensors with very special, simple things. Okay, so now I have to say, what is the covariance matrix? Right, what's the covariance matrix? So now I'm ready for that, and I'll put it here. That's the final topic for today. So the covariance matrix. So I'm saying matrix because I'm just going to have, the covariance matrix. Yeah, it's going to be 2 by 2, or for 2 coins. So it is a matrix. For 3 coins, it will be 3 by 3, but it is a matrix. Okay, so how is it defined? And what am I going to call it? I think I'll call it V because really the key idea is variance. Covariance is telling us that we're also interested in the joint outcome, an X and a Y. Okay, so it's a variance. So I'm going to add up over all possible I and J, all possible outcomes. Yeah, that's not right. All possible Xi and Yj. So I'm running these 2 experiments at the same time. From experiment 1, the output's an X. From experiment 2, the output's a Y. Then what is Pij? What does that symbol mean? That's the guy in our 2 by 2 matrix, like that one or that one, depending on the gluing or not gluing. So Pij, this is, let me say what it is. This is the probability that x is xi, and that the second output, that this is yj. And let me give you a second example to keep in mind. Suppose I'm looking at age and height. So suppose x is the age of the sample, the person, and y is the height. Then I want to know, so what fraction have a certain age and a certain height? It's I'm looking at every pair, age and height. Age 11, height 4 feet. Age 12, height 5 feet. Age 11, height 5 feet. Each combination. So Pij is the probability that these will both happen. Both. So what could, I'm going to add more to it here. But that joint probability is really important. So I'm going to ask you more about that. Suppose that I take these Pij's and that I add up P1j plus P2j plus P3j. In other words, I sum the Pij's over I. So I'm looking at a row I of my matrix. So so let me ask the question. Maybe I have to put it somewhere else. What means, what's the meaning of the sum of Pij over the i's? What does that quantity look like? So that's a probability. Pij is the probability of getting a certain I and a certain j. But now I'm including all the i's. So what am I seeing there? Pj, thanks, Pj. This is Pj. That's the probability of seeing j in the second guy. Because I had to see something. If I see j in the second one, I'm allowed to see anything here in the first one, but I'm adding those all up, so that's the point. Those would be called the marginals. In my matrices, I would be adding up along a row or adding up down a column. Those are called the marginals of the joint probabilities. So the marginals would be the individual probabilities, Pi and Pj, in the case of two experiments going on at the same time. Yeah, it's just like new ideas. Everything today has been sort of straightforward, but it's different. Okay, now I'm going to complete the definition of this covariance matrix. So it's going to be, I want to have a square. So it's going to be, and it should be, this is between x and the mean of x. Mean 1, I could call it, or mean of x. And y, the distance from the mean of y, times, so it's going to be column times row, same x minus the mean of x, y minus the mean of y. xi, yj. So can you look at this formula? So this is with two experiments, two coins, two experiments. I get a 2 by 2 matrix. Everybody sees that, a column times a row, 2 by 2 matrix. And let's just see what would be the 1-1 entry in that matrix. This is the covariance matrix. So what is the 1-1 entry in that matrix? So the 1, 1 entry is coming from that times that, which is that thing squared, times all the PIJs, add them up. What do you think I get for that? I get the variance of the X experiment, the standard variance of the X experiment. So V, I have to tell you what V is now here. V, this is V, 2 by 2 matrix. Up here I get the variance of the X experiment. What do I get down here? The variance of the Y experiment by itself, because it's Y's times Y's that give me the 2, 2 entry. So this is just sigma Y squared. Sigma Y squared. Okay, but the novelty is the 1, 2, and it'll be symmetric. So it's a symmetric matrix. So this is V transpose. We have to see here. So I have Pij times the distance of this guy times this guy. That's what's going to show up in the 1, 2 position. It'll be in row 1, it'll be in column 2. It's the X, it's the distances. So what will it be in the case of unglued coins, independent coins? 0. I mean, I'm just feeling like 0. I haven't done the computation, but I know that when I have independent experiments, then this covariance, which everybody would write as sigma xy, and it's the same here, it's symmetric, sigma yx if you like. So those subscripts are telling me that the sum of the p's, joint probabilities, times the distance of x from its mean, the distance of y from its mean, added up over all the possibilities. So the case of unglued coins, the case of independent ones, in that case, those are 0. Maybe worth just writing that out. You would get 0. So you have a diagonal matrix. The diagonal matrix is just the separate variances, because that's all. The 2 independent experiments are independent, so all you can really expect information is sigma x squared and sigma y squared. But if the 2 coins are glued together, then what? If the 2 coins are glued together, well, let me just say, because time is up, this matrix will be singular. If the 2 coins were glued together, this would be, the determinant would be 0 here. The sigma xy in the glued case would be squared, would be the same as sigma x squared, sigma y squared. Actually, we're probably getting all these 1/4, and that would make sense. So the case of so I'll just end with this statement. This matrix is positive semi-definite always. Positive semi-definite always, because it's column times row. We know that's positive semi-definite, and it's multiplied by numbers greater or equal 0. So it's a combination of rank 1, positive semi-definite, so it's positive semi-definite, or positive definite. It's certainly positive definite in the independent case when it's diagonal. And the totally dependent case, when the coins are completely stuck together, that will be the semi-definite case when these entries would all be the same, actually. In that case. So that's a first look at covariance matrices. It brought in tensors, it brought in joint probabilities, it brought in column times row, it kept symmetry, and we recognized positive definite or positive semi-definite. So in between, coins that were partly glued, partly independent, but not completely independent experiments, then this number would be smaller. The determinant would be, this wouldn't be 0, but it would be smaller than these numbers. Yeah, okay, I've run 4 minutes over. You're very kind to to say. So have a wonderful break, and I'll see you a week from Monday. Good. Thanks.